Welcome to this session of CS 712. Today I'm going to talk more about NFAs and DFAs. So the basic theorem here is that we don't need the non-determinism actually. That any non-deterministic finite state machine can be transformed to an equivalent deterministic machine. And it's actually a constructive proof. There's a key idea that we call the lambda closure. The lambda closure of a state S is that state S plus all the states that can be reached from S by using only lambda arcs. So the way I like to think about this is we think of a state in a new machine, which again is going to be deterministic, and it's sort of a simulation of all states in the original machine, which was non-deterministic, all those states that you could be in at this time of consuming the same amount of input. So again, last time I talked about non-deterministic machines. One way to think about them is sort of they spawn copies of themselves. Every time they come to a fork in the road and they can go multiple ways, they create a copy to go down each path. And what the subset construction idea is, it's forming these lambda closures, which is basically tracking where all those copies of the machine could be, the states that they could be in after they've consumed the same amount of input. And I think the best way to just see how this works is to work an example. And this will require us to sort of back up and review a little bit of what we did last time, because I'm going to start with a regular set here. And the first thing we need to do is draw the non-deterministic machine that will match that set. Again, that's another construction, right? So let's go ahead and do that. I'm going to start in some start symbol. I'm going to start in a start state, which is really modeling this alternation here in the middle, right? I'm going to either go this way or that way. Again, the parentheses sort of make clear the order of operations. So the first thing I'm going to do is have two lambda arcs. And I'm going to have to number these states. I'm going to have to draw my circles a little bit bigger. That's state 0. Let's say the start state is state 0. And up here, we're going to do the left-hand side of that alternation. So I can match an A, get to state 2. When I'm in state 2 now, I can match 0 or more C's. And then from state 2, I can exit with a B to go to state 3. That's really 3 states to match the inside here of that parenthesized expression, right? Match an A, I can loop on C as many times as I want, including 0, and then go on and match the B. Then let's model that star. And we saw how to do that with lambda arcs last time. I can skip it altogether. That's the 0 repetition. And once I get to state 3, I can come back to state 1 and do that as many times as I want. So 0, 1, 2, 3, as many times as I want. So that's a finite state machine for that portion to the left of the alternation here. What about the right-hand side? Now again, I've got an alternation on the inside and then these two subcomponents, if you will. So again, I'm going to come down here, have a state here with 2 lambda arcs, again modeling alternation. This alternation, and then I have the B on the left-hand side of the alternation. And the B and the C on the right-hand side of that alternation. At this point I realize I forgot to number this state. That's going to be state 10. And I'll bring the two alternations back together in a state 11. And then I have a cleaning star around this lower alternation. So again, I'm going to have to put some arcs, some lambda arcs in, one to return, and one to skip, I guess. Okay, again, modeling that star, so I can skip it, that's 0. Or I can go through one of the alternations. Again, I've forgotten to put some lambdas on here. And then return and go through as many times as I want. And finally, I have to bring this alternation back together again. And that becomes a final state. Either leaving the left-hand side alternation or leaving the right-hand side alternation. Okay, so again, that's a review of what we did last time, where I can go from a pretty straightforward algorithm to go from a regular set to a non-deterministic finite state machine. And what I want to do now is I want to squeeze out the non-determinism. All right. So I think what you're going to want to do, probably if you haven't done this already, is pause the video and get a copy of this slide, because I'm not sure I'm going to be able to fit everything on one page here. So you probably want to be peeking back at this one while I write on a new piece of paper in order to do the minimal finite state machine. Sort of a moment of truth. I should have thought about this ahead of time, obviously, but can I fit the deterministic machine down in here? I guess we can try. Let's try it. What the heck? All right. So right off the bat, we got to confront the idea of the lambda closure. Because what we're going to do now is we're going to build a deterministic machine that's modeling the behavior of that machine. So this machine is going to have a start state. And I'll put a circle around it later because I'm going to have to write a bunch of numbers in it. So we know that the start state in the new machine will include the start state for the old machine, right? And the question is, for lambda closure, is what other states can I reach from state 0 up here without consuming any input? So these are the lambda states that I can reach from 0. So I can reach 1. I can reach 10. But state 1 can actually reach state 3, this arc. State 3 can come back to 1. We already have 1. 3 can go to 12. I can't get anywhere. However, I still can, from 10 I can get places. So I can get to 4. I can get to 7. I can also get to 11. And I think that's it, because from 11 I can get to 12, but I already know about 12. So in fact, that's my start state in the deterministic machine. And again, it's modeling everywhere I can get to from the start state here without consuming any input. Okay. Now state 12 is a final state in the original machine, so this state has to be a final state also. So that tells us that lambda is in this language, which is true, right? I can get from here to there without consuming any input by following these lambda arcs. Okay. All right, so that's my start state. Now I want to explore on all input symbols, where can I get from this state? So let's start with A. On A, where can I go? I have to look, where am I? I'm in all these different states, so I sort of have to explore. In state 0 from A, I can't get anywhere. State 1 with an A, though, I can get to 2. State 10 on an A, can't get anywhere. State 3 on an A, can't get anywhere. State 12, can't get anywhere. State 4, I can get to 5. State 7 on an A, can't get anywhere. State 11 on an A, can't get anywhere. So state 2, 5 is going to be in the new machine. Neither 2 nor 5 is a final state, so this is just a normal state. Okay. Now let's look at B coming out of this state. Again, on 0 on a B, can't get anywhere. On 1 on a B, can't get anywhere. 10 on a B, 10 on a B, can't get anywhere. 3 on a B, can't get anywhere. 12, can't get anywhere. 4 on a B, no. 7 on a B, though, I can get to 8. 7 on a B, I can get to 8. So let me go this direction, I guess. Get to 8. 11 on a B, can't get anywhere. So 8 is going to be a state, but you know, I've realized I've screwed up already. State 2, 5, I really should have explored. Once I got to the 2, 5, I have to do the lambda closure of that. So can I get anywhere from state 2 on lambda? No. Can I get anywhere from state 5 on lambda? No. So I actually lucked out there. There was no additional states to add. Because again, I'm modeling, you know, where I can be by consuming the same amount of input. So once I arrive here on the A, I have to think about, can I get anywhere from these states 2, 5 on lambda? But I couldn't, so I lucked out there. I've got to do the same thing about 8. Right, I got down here on an 8 on a B, but there's no lambda arcs out of 8. So in fact, 8 is going to be a state by itself, and 8 is not a final state in the original machine, so it will not be a final state in the new machine. How about C from the initial state? 0 on a C, no. 1, no. 10, no. 3, no. 12, no. 4, no. 7, no. 11, no. So C actually is an error coming out of this initial state. Okay. So at that point, I'm done with this state. So I usually like to track that by just a little check mark here to remember that I've processed that state. So basically, the algorithm is I'm going to be pushing these states in a queue or on a stack and just exploring them one at a time. Okay. You can think about, will it terminate? Well, yeah. I mean, there's a finite, although large number of potential states. Right? At most, I can have the power set of the original sets. Sorry, the power set of the original states. Worst case. So I will eventually. The algorithm must terminate. So let's go to 2, 5 now. Where can I get on A from 2? Nowhere, I guess. Where can I get an A from 5? Nowhere. So A from this state would be an error case. How about B? B on 2 could go to 3. How about 5 on a B? It could go to 6. And now I have to do the lambda closure, because from 3 I can get to 1, and I can get to 12. From 6 on lambda I can get to 11, which can get back to 10, which can get to 4, which can get to 7. All right. 12 is a final state, so this is going to be a final state. Okay, but how about C out of 2 and 5? Well, I can go to 2. What about C from 5? Can't go anywhere. So again, I'm going to go to a new state. C is going to go to 2. Before I drew the circle around it, I should have done the lambda closure. Again, I'm going to luck out, though, because there's no lambda arcs out of 2. So in fact, that will be a state. Notice I can, I'm modeling 2 different things. Even though 2 is inside 2, 5, I don't combine these because it's 2 different states in the new machine. Either I'm in 2 and 5 simultaneously, or I'm not. And so that makes it a distinct state in the new machine. Okay, I think that means I'm done with this one. I'm sort of doing these in random order, so I'm going to go over here and do this one now. What about on an A? From 3, can't go anywhere on an A. 6 on 3, can't go anywhere. 1 on an A can go to 2. I got to remember that because it could be one of these 2 states. 12 can't go anywhere on an A. 11 can't go anywhere. 10 can't go anywhere. 4 on an A could go to 5. So now I can go to either to both 2 and 5 from this state on an A. 7 can't go anywhere. So in fact, it's a back arc here, right back here on an A. What about on a B? 3, again, can't do anything. 6 on a B, no. 1 on a B, no. 12, no. 11, no. 10, no. 4, no. 7 on a B, though, I can go to 8. So that means I've got to draw an arc around here. I think for layout purposes, I'm going to go around the bend here. Come in the back door. That's on a B. Okay. Again, I should do the lambda closure of 8, but I think I subconsciously knew there was no lambda arcs there, so that was a state by itself. So one last alphabet character to consider here, C. 3, no. 6, no. 1, no. 12, no. 11, no. 10, no. 4, 7, no. So I can't go anywhere on a C out of that state. So that takes care of that case. Okay. What state should we do next? I guess I'll do state 2. State 2 is an easy one to do because there's only one state. It only has an arc. Well, it has B and C, I guess, is an arc. So no A, though. So B could go to 3. Could be part of this one, though, but I don't think so. I think it's going to be a separate state. Let me try that out. B goes to 3. I do the lambda closure of that. I'm going to get 1, 3 again, and 12. And 12 again is a final state in the original machine, so it's going to be a final state in the new machine. C on 2 is a self loop, and there's no lambda closure, so that is just like that. So that takes care of this one. So let's pick this one up while we're at it. 3, 1, 2. Again, 3 on an A, can't get anywhere. 1 on an A, though, can go to 2. 12, I can't go anywhere. So it looks like the A is a back arc like that. That takes care of that state. So I've got everything done. I guess I'm going to have to go down and do this 8 now. Okay. So again, 8 is a single state, so I should be able to do that easily. I can sort of optimize here. I can see there's no A out of 8, there's no B out of 8, so 8 is going to go to 9 on C. 8 is going to go to 9 on C, so let's model that by coming out this side perhaps. I've got to do the lambda closure of 9. So it goes to 11, it goes to 12, 11 comes back to 10, 10 goes to 4, and 7. 12 is in that set, so it will be a final state in the new machine. And that's all that can happen out of 8. So that's done with 8. So now let's take a look at this one. On an A, 9, 11, 12, 10. They only have lambda arcs. So 4, A goes to 5. And in fact, 5, lambda closure of 5, there are no lambda arcs out of 5, so that's going to be a set all by itself. It's not a final set. How about on B from this state? Again, 9, 11, 12, 10 only have lambda arcs coming out of them. 7 though, 4 doesn't have an arc on B, 7 though does, it goes to 8. So that's a back arc like this. Right, we're talking about B here. Okay, what about C? Again, these only have lambda arcs on the top, 4 and 7. No, there's no C arcs. Okay, so it takes care of that state. So now we have to look at 5, the set containing only 5. So 5, again, it only has a B arc coming out of it, which goes to 6. Lambda closure on 6 is going to be 11 and 12. From 11 we can get to 10. From 10 we can get to 4 and 7. Again, I've got to look and see if I've seen that before, but I think that is a new state. I haven't seen that particular subset of these states before. And 12 is in there again. So this is that's not looking very pretty, is it? Not very good circles anymore. But it is a final state. And that's all we can do with 5. So now we're looking at 6, 11, 12. Ten, 4, and 7, this state. It's the only one left, right? So on an A out of 6, again, 6 only has lambda arcs, 11, 12 only have lambda arcs, 10 only has lambda arcs, but 4 on an A goes to 5. 7 can't go on an A, so it's actually a back a back loop. On an A, I can see I forgot to label this arc, so on 5 that was a B there. Alright. How about a B, 6, 11, 12? Again, 6, 11, 12, and 10 only have lambda arcs. 4 can't do a B, 7 can go to 8 though. So this one has an arc back this way. That's on B. And what about C? Again, 4 and 7 is where the action is. All the rest, the other 4 states only have lambda arcs, and C is not an option for 4 or 7. Okay. So, and that finishes the last set that needs to be processed. So, in fact, that is a deterministic machine that's equivalent to the first one. And maybe we should just quickly do a string, process a string, and see what we think. So what's a string that's recognized by, that's in the set described by this regular set? It's in the language described by this regular set. So let's do, A, C, C, B, A, B. How about that? Let's just verify that in fact it's in the first one, right? I can come up here on an A, I go here, I can do 2 C's, a B, come back, do an A and a B, and terminate. So it is, in fact, in the language recognized by this machine. Let's go down here. A, C, C, B, A, B ends up in a final state, so it works. How about another one? So how about start out in an A, do an AB, do an AB, and then do a BC. Looking for something that the first part shares both of the alternative sides of the machine. So let's just verify that's, if I got that right. I can come up here, A, B, come back around, go A, B, come back around, but now I get stuck. So in fact I went the wrong way. So let's try down here. A, B, come back around, A, B, come back around, B, C, finish up. So in fact it is recognized by this machine. So let's see what happens with the new machine. I do A, because I won't have any choices down here. A, B, A, B. Then I come round to the bottom half. All of a sudden there's only route is to come sort of down to this bottom half now. So I come over here on B, take the C, and I'm done. I'm in a final state. Okay. So again, that illustrates the subset construction algorithm, which is the algorithm for squeezing out the non-determinism and producing a deterministic machine. What we'll do next is we'll look at another algorithm that actually will take a finite state machine and squeeze out all the extra states. It'll actually minimize the finite state machine into an equivalent machine with the minimum number of states necessary to recognize the language. But for now, let's stop here.